This is CNIT 126, and I just want to mention, if you're in any of my classes, please come to the Hacking Club on Saturday. You can come physically, or you can connect via Zoom. This is Dave Porcello, who gave a hacking workshop last semester, and it was very popular. It's very good. He wants to give a frequent, perhaps weekly hacking club, and so it's going to be at 10 o'clock in the multi-use building on Saturday. Hopefully they will have resolved whatever crisis is going on over there now. If not, we'll probably have it in the science building, but I'll put a note on this webpage if I have to move it. Anyway, that'll be happening Saturday at 10. So it's worth extra credit if you want to go to that. And in a couple weeks comes the job fair. That happens every semester. If you're looking for a job, or you think you might be looking for a job in a couple semesters, attend this, because the people that are hiring give presentations explaining what they want, and you could go there just to find out what they want and then go take those courses to prepare for those jobs. So it's valuable even if you're not in the market for a job right now. Anyway, this is 126. We're down to the third class, and we're going to talk about x86 disassembly. So we've already talked about the basic techniques of malware analysis. There's static analysis, where you look at malware without running it, finding things in it like the strings, or sending a hash value up to virus total to just see if somebody else figured it out for you. Then there's dynamic analysis, where you run it and see what it does, which is easy, but not very thorough. And disassembly is where you really get all the code, and you can see in principle everything it does, but you have to read disassembly code, which is kind of hard to read. So computer programming has many levels of abstraction. Typically, anybody developing code writes in a high-level language like C or Java or Python, and then they compile it down to machine code, and usually they remove all the symbols. So you do not have the names of variables or the names of routines or anything down here in the machine code, and that's the executable code that you distribute. So the malware analyst has to read this binary machine code. So what you do is you disassemble it to this somewhat readable assembly code, which is easier to read than this binary stuff, but it's a whole lot harder to read than high-level stuff like C or Python. So you have to learn how to read this language, which is very close to the hardware and pretty alien at first. So here's some levels of abstraction. You got the hardware itself, microcode, machine code, and various types of languages. So the hardware is, for digital computers, it's XOR, AND, OR, and NOT gates, where you feed in voltage signals, and if they're both high, it treats those as 1, and if they're both low, it treats those as zeros, and you combine them bit by bit. And this is all your processor is doing, millions of these little gates that take in a few bits and do a simple operation on them like AND or XOR. Microcode is the firmware that runs on the hardware, and typically not important for a malware analyst, but it's important for people who are designing embedded devices, like Internet of Things devices, like thermostats and Raspberry Pis and stuff. You have a little gadget, and you have code designed in the gadget to do its essential features. And the machine code is the actual binary code that runs on the processor. This is what's really running on your machine. And assembly code is the assembly language is just a way for a human to read machine code. And this is where we're going to spend most of our time working at the assembly language level in this course, because this is typically the highest level language that you can recover from malware. All right. And then, of course, high-level languages like C and C++ are what normal developers develop in. And there are interpreted languages that aren't even compiled down to machine code. They're interpreted line by line how they run, like Python, so they run slower. This is like bash shell scripting. It's another way to encode stuff. One thing that happens here is you can have things like Java and .NET that are compiled not down to machine code, but to bytecode, which is a assembly-looking language that is independent of the hardware. And then underneath that, you run something like a Java virtual machine, which takes the bytecode and turns it into machine code. So it's a strange little way. The whole point of this is you could write something in a .NET language or in Java, and it could run on many different machines. You could run it on Windows or Linux from the same source code. Now, it runs really slowly, and it's buggy, but this is what a lot of people do because they want to be platform independent. You save time on your developers. You don't have to write a Windows version and a Mac version. So what we're doing is reverse engineering. We're taking a finished product that's executable code that is delivered as malware, and we're trying to reverse it to figure out how it works and how it was made without the source code. So you disassemble it from the binary machine code, you get assembly language, and the most popular disassembler has been IDA Pro. We'll use it in a later project, but I put it off towards the end because it's pretty irritating and confusing to use. So we're going to use easier tools first. And so there's three main parts of assembly language that matter to us. 32-bit Intel is the most common, or at least it was a few years ago. 64 Intel is now pretty much the standard, and that may be the most common one now. These two are, and soon, like I say, ARM is coming up. ARM is getting more and more popular. Those are the three we're going to use mainly in this course. These others are pretty much hardware that's not used very often. So x86, you have a central processing unit, and it has a small number of registers, which are storage units right on the chip that are really fast. Then it has an arithmetic logic unit that performs the calculations on the data, and a control unit, which fetches execution code from RAM. So it fetches an instruction, feeds it to the ALU, it runs it on the registers, and maybe sends it out, input-output to things like the hard disk or the monitor, and then it just fetches another instruction, and off it goes. So that's the control unit, registers, and the ALU I've talked about there. And then you have RAM. RAM is just a whole block of memory, addressable typically these days 4 gigabytes or something of RAM. And so you've got low memory going up to high memory, and each program, when it launches, gets allocated by the operating system a certain area of RAM to use. So each program has its own piece of RAM, that's its own allocated part of memory, and it has to read and write only in that region or you'll get an error. So there's static data that doesn't change while the program is running, and sometimes they call it global, available to any part of the program. And there's code. These are the instructions that tell it to do things like push and move and jump. And then there's a heap. The heap is an area of dynamic memory which changes during program execution, where you allocate some memory, use it temporarily, and then free it, and then reallocate the memory for another use later. So this is where your temporary scratch pad for things while your program is running. And then there's the stack. The stack is used for functions for when you call a function. You want to stop partway through a function and call another function. So you have to set up its own little bit of memory just while it's running. And when it's done, you're going to release that memory and go back to the calling function. So instructions are in this structure mnemonic followed by operands. The mnemonic is the first part, move, and here's the operands. Move 42 to ECX, ECX being a register. Move ECX is B9 in hexadecimal. It takes 1 byte to code that instruction, but the value 42 is 4 bytes long because we're using a 32-bit processor in x86 code. So it looks like this, and it's little endian, which means the least significant byte comes first, and then the higher bytes. So the number 42 in hexadecimal, which is 66 in decimal, because it's 4 16s plus 2, looks like this, 42000. All right, and that's the complete instruction. B9 is move into the ECX, and the thing to move in there is 42000. So there's your assembly language instructions, mnemonic, destination, and source. This is the Intel format, which is the most common way you look at Windows assembly code. On Linux, they often use AT&T format, where these two are reversed. Just to make sure you're always good and confused, when I look at code and I can't tell right away, I look for a immediate value, because you can put 42 into something, but you can't put anything into 42. So whatever you see an immediate number like this, that's the source. And once you spot one of them, you know which one of these formats you have. So let's try a Kahoot. I should have them ready to go here for A. All right, I think I need to move it over a little. All right. Good. Is the undo command in Word a representation of a stack? Well, I've heard people describe it as a ring. It's kind of like that. It does have a sort of similar effect at a higher level. This came up by last semester in my Python class, and they called it, I think they said it's implemented with a ring buffer, but I didn't really, a ring list, but I don't really understand that. I think a stack would make a more reasonable description of it. That book said it was a ring, but I really don't believe it, because it's not like if you undo enough times, well, you get back where you started. It's one way. You undo, and you're just going back to the past. You're not ever going to end up in the same spot. You do not need to sign up for the hacking club. Just show up or tune in on Zoom. Good. Yeah, I think so, and bibliophobe. Do we get penalties? No. Go ahead. I'm going to start this, but go ahead and turn in projects even if they're late. You'll still get most of the points, maybe all the points. All right, so what portion of this is the mnemonic? The first part, move, all right? All right, what language does the processor use? Yep, binary machine code is all it knows. These other things are just things for humans, but the processor runs raw binary machine code. That's all it can do. All right, so what utility turns a high-level program into an executable file? That's a compiler. Now, an interpreter turns individual statements into machine code one at a time, but it doesn't create an executable file. That's a compiler. In Linux, you use GCC. In Windows, you use Visual Studio, most common compiler. All right, so what's the most common type of assembly language you find in malware? x86 is what the book says. That may be true. I haven't seen a recent test. I wonder if it's now x64 more common, but the general wisdom is it's x86. I haven't seen any recent studies to see which of those is more common these days. All right, and where are the local variables stored? On the stack, they're used only while one function is executing, the local variables, and then forgotten when it's over, and that's what the stack frame is for. It stores all the local variables that you're using only while running one function, and that memory is released for reuse when you return back to the calling function. OB1. All right, you have to tell us who you really are if you want your points, and the same for IDK. That's a real name. He's going to get his points. All right. So, let's go on here. Okay, so like I mentioned, big endian and little endian. Big endian is the normal way you write numbers. So 42 as a 32-bit value would have a bunch of leading zeros and then 42. This is the logical way to write it, where each digit on the left is 16 times more significant than the other. This is the number of ones, this is the number of 16s, this is the number 16 squared and cubed and so on. But for some reason, Intel uses little endian, which is really weird. You take the 42 and you move that byte over to here, so the least significant bit is the 8th bit here. And the next most important bits are the rest of these 8, and then you go to this one and back through these 8, and this one back through these 8, so it's pretty illogical, but that's the way it is. The bytes have the little byte first, but within each byte, the bit on the right is the least significant bit. That's the way it is. All right, so IP addresses, however, have to go over the network in order. It's designed for that, and this is for a big good reason. This is why the original networks had A, B, and C, because you could tell from just the first few bits of a network address what category it was in, and that was used to route it at a time when networks were very slow. And you would actually want to be processing it while only a few bits have come through. So it has to go through in the right order. But it'll be stored in RAM this way, which could give you a headache. So immediate values in assembly language will have just a number. This 0x means hexadecimal, otherwise it's base 10. Your registers are things like EAX and EBX, and memory addresses have brackets around them. So you have bracket around EAX means you take the 32-bit value in EAX and interpret that as a memory address, and you go fetch the contents of that memory address. So here's the registers. You have EAX, EBX, ECX, and EDX. Those are the general purpose registers. Then you have the base pointer and the stack pointer, which are the bottom and top of the stack frame used by the current process. And then you have ESI, which is another general purpose register often used to index through things like a string. And then you have flags, which you almost never refer to directly, but it includes information like whether the last instruction resulted in a 0 or greater than 0 or less than 0, so you can do branches. And then you have the instruction pointer, which you don't write to directly. It's controlled by the control register, control unit, that feeds the instructions in. This is the address of the next instruction to be executed. So the goal of a hacker is to gain control of the EIP, because then they can redirect it to execute code which is different than what the developer intended to execute, and that's how you take over machines. So that's the same thing. All right, status flag. There are some things called the segment register, by the way, but we almost never worry about them or talk about them. So the registers are 32 bits in size. You can, and because you might possibly be running 16-bit code left from like MS-DOS, which I don't think anybody is, but in case you are, the processor supports it, you can refer to the lowest 16 bits of the register in case you want to run 16-bit code, or even the lowest 8 bits of the register, or the next to lowest 8 bits if you want to do 8-bit code, which hackers do sometimes just to make their code easier to inject by removing the null bytes. But normal programmers would never bother with 16 or 8-bit instructions. They're inefficient. All right, so here you are. There's the full 32 bits. Here's the lowest 16. Here's the lowest 8, and the next 8. Those can be referenced in instructions, but only a hacker would use these typically, or somebody running really old programs. All right, so typically the EAX through EDX can be used for any purpose. There are a few special traditions, like usually the return from any function goes in EAX, and if you do multiplication and division, then they need more than 32 bits, so they do things like use AAX and EDX in a combination to store a 64-bit value, but you don't that often do multiplication or division in assembly code, certainly not for the simple stuff we're doing. There's the flags for the status register, which keep track of things like whether the last instruction resulted in a 0 or not. Here's some example 0. Here's carry because you added things and they got bigger than 32 bits, and so on. We're not going to use any of them directly. We're going to use them indirectly with things like break. There's the instruction pointer. If you get junk in the instruction pointer, like you inject ASCII values like A, that will usually cause the program to stop because it's an invalid address. That will be an error. All right. So here's a few simple instructions. The most common instruction by far is move. This is mostly what you have. Move source to destination. This will move stuff from a register to another register, from a register to memory, from immediate value into register or memory, that sort of thing. And remember, indirect addressing, the brackets mean you're referring to somewhere in RAM, and whatever's inside here is how it calculates which RAM address you're talking about. So here's move EBX to EAX. Here's move 42 into EAX. Here's move that specific RAM location, 4037C4. Go look up whatever's in there and put it in EAX. Here's take EBX as an address. Look up that address in RAM. Find whatever's in that RAM and put it in EAX. And here's something you'll see a lot. EBX plus ESI times 4, this brings up an issue that is annoying but true. The RAM numbers the bytes one by one. Each byte is only 8 bits long, so if you have 32-bit registers and a 32-bit processor, then when you're reading RAM, you're reading it 4 bytes at a time. So if you want to move a whole block of RAM somewhere, you have a base you're started at, and then you have an index like ESI counting, and you move it 4 bytes at a time. So this is a very common construction. The start of, say, a string, and then we're going to have ESI count through some, from 1 to 10 to move a 10-character string. We're going to jump up by 4 bytes every time. I guess it would be a 40-character string, but anyway, the point is each move operation moves 4 bytes, so you move forward 4 at a time. All right. Then this is a really screwy one in the Intel processor. You can load effective address of EBX plus 8, and I've always found this frustrating, but there are certain commands that don't exist. Like you would like to take EBX plus 8 and put that value in EAX, and that instruction does not exist. You'd have to do it in a few separate steps, but you can do it this way. This calculates an address, and then instead of looking that up and finding the value of the RAM, it just puts the address in here. So this brackets are here, but it doesn't actually look up the contents of that RAM. So this is a little confusing. But anyway, that's what it has. Now a move would have taken EBX plus 8, loaded that data from RAM, and put that in EAX. But LEA just calculates the address. Sort of screwy instruction, but that's the way Intel did it. All right. So here's an example. EAX has 0, EBX has this. And if you look at that address in RAM, you have this. So this one, load effective address, EAX EBX plus 8, would take this number and add 8. So it'll put 830048 into EAX. It does not look up what's in the memory. It takes the address and adds 8 for load effective address. But move EAX bracket EBX plus 8 takes this address, goes up to memory, goes forward 8 bytes. All right, oh, I better turn this on. And then loads this quantity from memory, which is 20, and puts that in EAX. So it's important to understand this, and confusing at first. All right, so you have subtract and add, increment, decrement, multiply and divide, as you'd expect. And you have NOP, which is like 0 in arithmetic. At first it might seem like this senseless thing to have. Turns out to be quite useful. NOP just does nothing. And the original purpose of it is there are certain instructions that must start at a certain location, like on a 4-byte boundary. So if the previous instruction was only 1 byte long, you need to fill in 3 bytes of padding, and you do that with NOPs. NOPs do nothing. Attackers use it to make attacks more powerful. They put in a NOP sled because when you inject code, we'll be doing it in the exploit development class, when you inject code, you now have to find the code you've injected, and often you can't figure out where it is very precisely. So to increase the chance of your attack working, you'll put something like 1,000 NOPs before the code. And now, all you have to do is guess within 1,000 bytes where it is. If you guess anywhere in the NOPs, it will execute NOP, 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 and then run the egg, which is the code you're trying to run. So this is one thing you can use to detect attacks, is you just look for NOP sleds. It's not something any normal compiled code would have, but it's something a lot of code designed by attackers have. So the stack is where you have information, data stored for a local function. And so it's last in, first out. You're running something like main, then you call a subroutine, and you allocate memory on top of that. And then if you call something inside the subroutine, a subroutine, like a dream within a dream, and you have a stack frame for each function, and as you return from them, you release the memory and pop up to the program before and the program before. And you do it with these registers. The top of the stack frame is the ESP, and the bottom of the current stack frame is the EBP. So push puts data on the stack, and pop takes data off the stack. So you enter a function with call or enter, and you exit with leave or return. So small functions might do one thing in return, like print. At the start of the function, there will be a prologue, which creates the stack frame by adjusting ESP and EBP. And at the epilogue, there will be instructions that remove that stack frame and restore the previous value of EBP. So you return to the calling function and restore the stack frame to the calling function stack frame. So this is the issue. You'll find the original function stack frame is here, then it calls, or there's the first, you start here, like in main, then, Oh, no, I'm sorry. This is the one you start from. Start here from main, then you call a function and you go down here. Then this calls a function and you go down here. Now the stack is 3 deep. You'll have these are all the frames available on the stack, and you'll be able to see that in the debugger. All right, and in the frame, you have variables and arguments and so on. And then at the end of the stack frame, at EBP, you have the old EBP's value. So when you return from this frame to the calling function, you'll restore the EBP from here, and then you have the return address, which tells you which instruction in here you were executing. And this is why you can take over the machine so easily. If you have a string variable here, and you're able to write past the end of it, you can overwrite other variables, and you can overwrite the stored EBP and the stored return address. And then when it tries to return from that function, it goes to the wrong address. Not an address chosen by the developer, but an address chosen by the attacker. That's how buffer overflows work. All right. There are conditionals to execute if commands. Test compares two values and to see if they're equal, and compare sets two. They're very similar. The difference is, and will alter them. This won't alter them, and I don't think compare will alter them either. Anyway, these are things you'll see. A test followed by a jump 0 or jump not 0 often implements an if statement. And here's branching. Jump 0 or jump not 0 are one. There are a bunch of other ones, but that's the point. So the combination of a test and a jump 0 or jump not 0 adds up to an if in a high-level language like C. So every C has a main function. In comes this is where the program starts, and it has arguments on the command line. You might just run the function with the name of the function, or you might have arguments after it, like copy. All the bash shell commands are C functions. So copy copies a file. See a copy, old file name to new file name. So there's 3 arguments in the command line, and those will be in this array of arguments. So if you copy foo to bar, you have 3 arguments. The first one is CP, the name of the program itself. Next one is foo, and the next one is bar. So let's take a look at another Kahoot, which is 4B. Guess that's it. Oh, okay. Thought there might be a few more. I'll wait a little more. All right. All right, so what does that instruction do? Yeah, it looks up EBX, treats it as an address, loads the contents of that address in memory, and puts it in EAX, the green one. All right, what command retrieves data from RAM? same as before. This one might confuse you. This loads the effective address of that calculation, but it doesn't retrieve the data from RAM. This one does. It treats EAX as an address and retrieves that location in RAM, its data, and puts it in EBX. All right, which command changes the size of the stack? Push adds more data to the stack, moving the stack pointer, causing the current stack frame to get larger. All right, which instruction is repeated many times in a buffer overflow attack? You often have a NOP sled, many NOP commands in a row. All right, what command retrieves data from the stack? Pop takes data off the stack, the way push puts data on the stack. All right. So, I stop this recording.